In this video, we're going to be learning about electric potential energy. What that means is we're going to be looking at things we learned in the past about electric fields and forces and applying work and energy to it. More specifically, we're going to be looking at electric potential in parallel plates. So two parallel plates that are charged and their electric potential. So let's first review what is an electric potential. Well, a Van de Graaff generator is an impressive electrostatic generator that is capable of producing enormously large static electric potentials, or volts. In fact, a Van de Graaff generator can produce millions of volts, leading to awesome displays of Corona lightning. But in our classroom sizes and what we use, we're just going to be looking at simple Van de Graaff generators, which only produce around 100,000 to 5,000 volts. So let's look at how a Van de Graaff generator creates an electric potential. So let's start off here. We have this comb, a metal comb that is connected to a voltage or power source. And then I have a rubber band that goes around like this, and there's another comb on top attached to that rubber band. What ends up happening is this power source is going to steal electrons from the rubber band, because remember, only electrons can move. And then this rubber band is going to be positive. Now what's going to end up happening up here is electrons from this dome is going to end up going down onto the rubber band to balance out that positives. And then we're going to go down here and we're going to disperse of other electrons if there's too many electrons on there to the ground, and it keeps on rotating. So eventually what ends up happening is, remember, all like charges repel. So that means the dome here is going to be full of positive charges trying to repel each other. So what ends up happening is when you touch it, the electrons from your body is going to go into the Van de Graaff generator, and a unique thing will happen to your body, just like this video I'm going to show you. So here's a video I got off the internet. We have this lady here touching a Van de Graaff generator. What ends up happening is electrons from her body is going to go into the generator. And as you can see, what's happening is her hair starts standing up. So that means this electric potential is creating work, causing her hair to move against gravity and stand up. In this video lesson, we're going to explore and learn how electric fields and electrostatic forces are related to work and potential energy. We'll also learn how to use these relationships quantitatively to solve some interesting problems involving electric fields, work, and energy. Basically, we're going to be learning about what's happening in this situation here with the Van de Graaff generator and the later, where we have electric potential creates an electric field, which then causes a force to do work over a distance, which is essentially creating potential energy. Let's now consider and review what we learned about potential energy in lessons before. So we know that from previous studies that work is done if we move an object in the direction of a force. So in other words, work is equal to force times distance. Now if we remember, the ability to do work is most of the time creating potential energy. So if I was to lift this mass over here up against the force of gravity at a certain distance, I would be creating a potential energy. So the work creates potential energy. We're transferring that energy to potential energy. So now how about we consider these two charges here? They are together. Now to separate these charges apart will create work. And that work is going to be potential energy because they will reattract to each other. So if I was to move this red particle away, the positive charge particle, I would have to do some work. Then, as soon as I release it, there would be a potential energy, which would then turn into kinetic energy as it reattaches or recombines with my larger source charge. So electric potential energy is the energy stored in the system of two charges of a certain distance apart. Electric potential energy equals the work done to move the charges apart. So I want you to look at this little fun animation I have here where we have a monkey. When is this monkey doing work? I want you to pause and say when the monkey's doing work and then come back. Welcome back. If you said it's where he is moving, or when the monkey's moving the little positive ball to the larger ball, you are correct. Now I want you to do the next part here. We're going to have to pause the video again. Can you think of other situations involving charges where we would need to do work? Think of the types of charges we have and their interactions. Which movements would involve work? So pause the video and we'll see if you're correct. Well, if you came up with 3 situations You are most likely correct. So we do work when we're forcing two positive charges together, like what the monkey's doing above, or if we're forcing two negative charges together. Another way we're doing work is if we're forcing unlike charges apart. Because remember, we're doing the opposite of what these charges want to do. Positive charges want to repel. We are pushing them together. We are going to be doing work or creating potential energy. Moving negative charges together, these are like charges, they want to repel. Moving them together is doing work because it's creating a potential energy. And unlike charges, they attract, so moving them apart creates a potential energy and causes work as well. Here is my first example. In my first example, we have a small charge moving from one position in an electric field to another position, which requires 3.2 times 10 to the negative 19 joules of work. How much potential energy will be gained by the charge? Now I look at this here. We know the amount of work is equal to my potential energy, because we have to do work against that force. Okay, we have to go against the electrostatic force here. So in other words, my work or my potential energy is going to be equal to my work, so my potential energy is 3.2 times 10 to the negative 19 joules. So now let's suppose we have two positive charges right here that are pushed towards this plate. Well, that's going to be twice as much work to push both of these identical positive charges as it would be to push one charge. However, just as much electrical potential energy is stored in each charge. So here's another example here. We have a potential difference of 10 volts. Now, we do 30 joules of work to pull these charges away. So each charge is going to be 10 joules of potential energy. Altogether, I have 30 joules of potential energy. So storing 10 joules of energy in one charge is the same as storing 5 joules of energy in two charge. It is often convenient to consider that just electric potential energy per unit charge at the location, we have a term for this called electric potential or voltage. Now that's a key thing to remember, that electric potential is the same thing as voltage. It is your potential difference, which is the energy per unit of charge at any given location. So the charge in electric potential energy stored per unit charge is the same thing as electric potential is change in electric potential energy divided by charge. So in other words, my volts is equal to my change in energy divided by charge, or what's to change in energy is the same thing as work divided by charge. So voltage or electric potential is work divided by charge. So here's my second question. Moving a small charge of 1.6 times 10 to the negative 19 coulombs between two parallel plates increases its electric potential energy by 3.2 times 10 to the negative 16 joules. Notice how it says electric potential energy, not electric potential. Determine the electric potential difference between the two plates. So let's look at what's given, what we're trying to figure out. First, what we're trying to figure out is my volts. What is given is we are given my charge, which is 1.6 times 10 to the negative 19 coulombs, which is the same charge as an electron or proton, and we know my energy or work is equal to 3.2 times 10 to the negative 16 joules. My formula for voltage, we said, the potential difference is the same thing as my work divided by my charge. So in that case, it's going to be 3.2 times 10 to the negative 16 joules, and that's going to be divided by 1.6 times 10 to the negative 19 coulombs, which is going to end up giving me a total of 2.0 times 10 to the 3 volts, which is the same thing as 2,000 volts. Okay? So now suppose the magnitude of the charge placed in an electric field were doubled. How much would the electric potential energy and the electric potential change? To help me understand this, I'm going to look at my equations. I know volts is equal to or my electric potential, is equal to electric potential energy divided by my charge. So if I double my charge, that's going to end up halving my volts. Let's rearrange the equation for energy to be isolated, which is the same as volt multiplied by my charge. In this case, if I double my charge, I'm going to actually end up doubling my energy. So let's look more at electric potential difference. Electrical potential difference is when a charge moves from one location to another, it experiences a change in electric potential between the 2 points. This change is referred to as electric potential difference. What does that mean? So if I have a point and it's getting closer to my source and they're opposite charges, we are actually going to be changing the voltage or changing the potential difference because the forces are going to change as we get closer. We're getting closer, so the field is going to change. The change in volts is equal to my final volts subtract my initial volts. So here's an example to help us through this. We have a small charge of 3.2 times 10 to the negative 19 coulombs, and it moves between two plates from a position with an electric potential of 2.0 times 10 to the 3 volts to another position of electric potential of 4 times 10 to the 3 volts. First, we want to determine the potential difference between the two positions. So if we move from here to here, the potential is going to be less, okay, because it already did some work to move there. We have less potential energy, so therefore my potential difference should be less as well. So how do I solve that? So let's look at A. First thing I'm going to do is, use my formula we learned. The difference in potential is equal to my final volts minus my initial volts. So I have 4,000 volts minus 2,000 volts gives me a total of 2,000 volts. Now let's look at what B is asking. B says the electric potential energy gained by moving the charge in joules and electron volts. We're going to get into what electron volts is here soon. First thing I want to do is to calculate the potential energy. To do that, I must use my equation. So my equation for this is my change in volts is equal to potential energy divided by charge. But I want to solve for potential energy. So potential energy is equal to my charge times my change in volts. So now I'm going to put in what we know. From above here, I know my charge, and I know my change in volts that we figured out before, which will end up giving me 6.4 times 10 to the negative 16 joules. But now we want to make electron volts. So I know 1 electron volt is the same as the charge of an electron, which is 1.6 times 10 to the negative 16 joules. So I want to figure out how many electrons fit in there. So I'm going to divide my total joules by the amount of charges of an electron, which will end up giving me a total of 4.0 times 10 to the 3 electron volts, or 4,000 electron volts. So that means we would need 4,000 electrons to make up that much joule, and that gives me my electron volts. One thing to keep in mind is when we're looking at two plates or two parallel plates, we know that positive field lines always go to negative. So then field lines between two flat parallel oppositely charged conducting plates are always going to be perpendicular to the plates. As we learned before, field lines radiate out from the source, so they must always be perpendicular, so we're going to tend to end up getting a lot of times straight lines. And these straight lines are going to be in a uniform motion. So between two flat plates, if we look here in between them, my lines are not any closer or farther apart. They're equidistant apart. So that means the field is of uniform strength. Same with over here. So no matter where you place a charge, the electric field will be the same numerical value in between two parallel plates. So the last thing we're going to do is we're going to try and figure out how can we find the electric field strength between these two plates. Well, most time we'll be knowing our voltage and the distance of the plates. Now, voltage is the same as potential difference, which means my potential difference is equal to my energy divided by my charge. Now, we know energy is the same thing as force times distance divided by charge. We know my field my electric field is equal to my force divided by charge. So how do I get rid of that distance? All I have to do then is divide by the distance of the plates. So once again, my electric field strength is going to be my change in voltage divided by the distance of the plates, because the field strength anywhere between these plates should be the same. So the unit conversions and cancellations will look something like this. So this is the main thing used, is volts per meter, but it also be measured in joules per coulomb per meter, or newtons meters per meter per coulomb, or newtons per coulomb. But we're going to tend to use volts per meter when we're talking about electric field strengths between plates. So here is going to be my first example. We want to calculate the field strength between two parallel plates that are 6 times 10 to the negative 2 meters apart, and the potential difference of the plates is 12 volts. So here I know my distance is equal to 6 times 10 to the negative 2 meters, and I know my potential difference is 12 volts, and I want to figure out what is my electric field strength. So I know my electric field strength is equal to volts divided by distance, which is equal to 12 divided by 0.06, which is going to be 200, and that's going to be volts per meter. So that's it for this video. Hopefully in this video you learned the relationships between electric fields and charges along with energy, as well as relationships between potential difference and electric fields and forces.